A couple class periods ago, I showed you how to draw a TXY or a PXY diagram using Microsoft Excel. In this video, I'm going to show you how to draw a TXY or a PXY diagram using Unisim software. The main advantages to using Unisim software is that you can model a non-ideal system a little bit easier than you could making hand calculations in Excel. The downside is there's a little bit more steps that are involved to it. So first, I'm going to choose a system to model, and I'm going to choose to model the ethanol water system because I know that it is non-ideal. So I don't expect a nice symmetric TXY or PXY diagram. So after I enter the simulation environment, I just did that before the video started, but that's File, New, and Case. Or you could click Control-N. Reminder that you do have to be connected to UF on the VPN in order to use Unisim software. So I want to add some components. So I want to click Add. And I said I was going to do ethanol and water. So ethanol, I happen to know, is the more volatile component. So I'm going to do it first. It really doesn't matter which one you do it first. But I'm used to having the more volatile component as component 1 or component A. And actually, it's not really correct to say ethanol is more volatile than water. In general, ethanol is more volatile than water, but because it forms an azeotrope, remember the volatility switches for certain compositions of water-ethanol system. All right, so this is the component list. I've now finished that. Remember, there's no OK button most of the times in Unisim, so you can just click the red X to exit. Next, I need to select a fluid package, and this is where you tell the software what model you want to use. So remember, there's tons of models that you can choose to use in Unisim. And I was just talking to Dr. Svoronos about this, about how would you know which one you want to use. It's really a bit of a trial and error process, unless you happen to know or unless you have some knowledge of which one to use. If I just pick one at random, let's try this one. So one benefit to using Unisim is if you choose a software package that is not recommended, it will flag that for you. So you should also know that if you choose to override this and click OK, it's not that big of a deal for me now, but if I were to model the system and then go back and try to change it to something that doesn't work, it will automatically remove that component. So say I already modeled the system and I wanted to go back and change the fluid package to see what else would happen. And if I choose this SO one, which is SO tabular, and I clicked OK, it would then delete ethanol from my simulation. And it would be a pain to go back and use. So really think twice before you decide to click OK and override the computer. So I need to find a fluid package that is going to work. And from my discussions with Dr. Svoronos, I happen to know that PRSV works pretty well for ethanol water. You could also choose the general NRTL, or you could choose the Margulies. I'm going to keep with the PRSV for now. This stands for Peng Robinson Suave somebody else. Peng Robinson Suave and V, I don't know who that is. Okay, so that's all I have to do here. Property package, I'm going to click all, and equation of state, enthalpy method option, we don't really need to worry about that. So click the red X, and we've got our components, we've got our fluids. We can now enter the simulation environment. And this green sheet is what tells me that I'm in the simulation environment. Now, for Unisim processes, you can only model continuous processes. So I cannot model a closed system to find the PXY or the TXY diagram. Remember, I'm not sure if I said that. We're trying to model or draw the PXY or the TXY diagram for this system. So the way I have to do it is I have to convert the closed process into an open process. So I'm going to vary the mole fraction of ethanol in my ethanol water stream by adjusting the flow rates. So I'm going to have one stream that is going to be water, one stream going to be ethanol. I'm going to mix them, heat them, and then separate them. So that's kind of a broad overview of what the process will look like. So I'm going to double click on my first stream, and I'm going to say this stream is going to be my ethanol stream. And here I need to specify some process conditions. So we have to choose if we want to do a TXY diagram or a PXY diagram first. Just for sake of argument, I'm going to do a TXY diagram first, and I'm going to do that by setting the pressure arbitrarily to whatever value I want. So let's do the TXY diagram at 1 bar, so close to atmospheric pressure. I also need to click a temperature here, but it really doesn't matter what the temperature is because the temperature is going to change as I heat it and as I establish phase equilibrium. So it doesn't matter what I choose here. Let's make it cold. Let's say 15 degrees C, just to break up from the monotony of always choosing 25 C. The last thing I need is to specify a molar flow rate. And in order to draw the TXY and the PXY diagram, I have to vary the mole fraction of ethanol from 0 to 1. So it doesn't matter what number I choose because I'm going to end up varying this. I'm going to show you how to do that in Unisim a little bit later, but I need to establish a first value. So I'm just going to say 0.25. I can pick anything I want between 0 and 1. And let's see, that should specify my stream, unless I've forgotten. Oh, I need to tell it the composition as well. So this stream is the ethanol stream. I'm going to make that 100% ethanol and click OK. And that should specify my stream. And I know that the stream is specified. Remember, the dark blue arrow means that I'm specified. Next, I need a stream of water. So this is going to be my water stream. I have to go into composition to click 100% water. Whoops. 100% water and 0% ethanol. Okay. Properties, I'm going to choose the same, conditions, I need to choose the same process conditions. So 1 bar, I could also type 100 kilopascals and 15 C. Now, I did not set a molar flow rate here because I'm going to vary what the mole fraction is by using a tool called the set key. So over in your toolbar on the right, there's a gray diamond with a green letter S in the middle. That is called the set key. So click on that. And what this does is it sets the value of a variable by using another variable. So I'm going to put it in between the two feed streams, double click it to specify it. So the target variable is going to be the one that I am varying. So I need to select variable. And I need to click, let's see, what variable I want to set the value of the water flow rate. So water, scroll down until I get to variable of molar flow. Click OK. And that is going to be based on the value of ethanol. So I also need to change in the parameters tab. I have to tell the software how I want the value of the water molar flow rate to vary based on the ethanol. So because I'm using it as molar fractions, I want the mole fraction of water to be 1 minus the mole fraction of ethanol. We've seen that many times in different contexts. All that says is that in a binary system that the mole fractions of the two components must always sum to 1. And I accidentally clicked out. So I need Y, which is my mole fraction of water, to be 1 minus mole fraction of ethanol. So you can read here, this makes a little bit of sense. It doesn't make a lot of sense when you first see it, but it's basically Y equals mx plus b form. So the multiplier is the coefficient of x. And I want my multiplier to be -1 because I want it to be 1 minus x. And my offset is my y-intercept. So I want that to be 0 such that it is 1 minus x. And you can see that in this equation there. All right, so I'm going to click out. And if I've done this correctly and I click on water, I should see that my molar flow rate is indeed 1 minus the molar flow rate of the ethanol. Remember, I set the ethanol at 0.25, meaning the molar flow rate of my water is 0.75. Perfect. So I've got 2 inlet streams. Any number that I choose for my ethanol will then also change the flow rate of water. So that's how I'm going to vary what the mole fraction is. Next, I need to mix these 2 streams. So I'm going to choose the mixer over here on my right and import that one. Double click it to set the inlets. I want to set inlets are going to be the ethanol stream and the water stream. And I want my outlet to be a stream that I haven't named yet. So I'm just going to call it mixed stream. And I need to set some parameters. No, I don't need to set parameters. I think that's it. I think that's all I need to do for the mixer. Yep, everything's blue, so that means it's okay. The next thing I need to do is I have to add a heater. So I'm doing a TXY diagram So I'm going to change or vary what the temperature is. So I'm going to click the heater, double click it again to set the inlets and the outlets, or the inlet and the outlet, both singular in the heater. Mix stream, and then my outlet I'm going to call equilibrium stream. I also need an energy stream here, so I'm just going to call this one duty. It's typically what I call the heater streams in process simulations like this. Now on the heater, I have to set parameters. And if we do a TXY first, remember the pressure is set in a TXY. So I need to set delta P is equal to 0. And let's see. What I need to set something else here. Okay, I don't want to set the duty, right? I want to specify something else. What I want to specify out of the heater is that I have phase equilibrium. And then I really don't care what the duty is. All I'm using this for is to heat the stream such that a certain temperature is achieved. So really, temperature is what I want to measure, not the duty. So to do that, I'm going to click Worksheet, and then the equilibrium stream, I need to set a fraction of the stream that exists as vapor. So if you look at mixed stream, vapor is 0 here, signifying that the mixed stream is completely liquid. And that makes sense because remember, I set the temperature as 15 C for the ethanol and the water. So therefore, the mixing stream doesn't have to be exactly 15 C. There's probably some enthalpy of mixing. And if I look at what the temperature is, indeed, I do find that it cools down some, cools down to 8.7. That's actually unexpected. I didn't expect it to cool down by that much, but it could be because of the model that I'm choosing. So all the numbers that I'm calculating in the software, remember, are based off of the model that I chose in the very beginning. Anyway, I need to specify that the vapor mole fraction is something. Now, importantly and paradoxically, it does not matter what number I choose, as long as I pick something between 0 and 1. So this is the fraction of the stream that is going to exist as a vapor. So no matter what I choose, again, I'm going to get the same curve. The only difference is when I plot the discrete points, I'll get different points based on the number that I choose. So I'm going to put in here 0.3. And I encourage you to try something different and then compare our answers at the end. So you try 0.7 and see what happens. Okay, and now I'm going to, okay, good. It turned blue, which means it's specified. It turned dark blue, meaning it's specified. And I don't really like the way this worksheet's laid out, but that's okay. I'll get over it. All right, so now I've got a stream that is in equilibrium, and in order to see what the compositions are, I then need to separate it. So I'm going to click the separator and put that. That's the last unit, so we're almost finished. My inlets is going to be the equilibrium stream, and my outlets, I need to specify some more streams, so I'll call it V and L. And hopefully I shouldn't need to specify anything else. So this particular separator just separates the liquid and vapor phases. So if I click out of it and I hover over it, I'm seeing that my molar flow rate is, I'm going to need to see the compositions here. So I'm going to double click, maybe. Okay, I had to click somewhere else, then click on it. If I click composition, it shouldn't quite be 0.25 and 0.75. It should be a little bit enriched in the ethanol. And perfect, that's exactly what I see. So that's what I would expect. So because I know that ethanol is generally more volatile, its mole fraction is greater than it started at the beginning of the process. Well, after the mix stream. So in the mix stream, if I click on the composition of that one, it's 25% ethanol, 75% water. And afterwards, I've done the phase equilibrium. Now I know that the mole fraction of ethanol has gone up in the vapor phase and down in the liquid phase. So now what I want to do is I want to vary the flow rate of ethanol, which is again going to vary the flow rate of the water by the set key. We're going to do this calculation many more times, and we're going to record what the mole fractions of ethanol are in the vapor and liquid streams, and then finally we can set them. I'm going to show you one more cool trick before we move on, and that is the table. So if I right click on, I'm sorry, it's not a right click, 1 minute. was a right click. So hover over, right click, show table, and that's going to bring up some parameters here. And this is going to make it easier to see. You don't really need to do this. I'm just demonstrating that if you ever want to monitor what the value of a particular variable is, you can do it with the table. So you can double click here. You can delete variables. So like molar flow, we don't really need to know for this case. So I'm going to remove it. Or you can add variables. So maybe I want to know what the component mole fraction of ethanol is. That would be useful to know. I can add that to the table as well. So I can do that, the same thing for L as well, the liquid. All right, I want to point out here that temperature and pressure are the same. That is to be expected. I should expect that in equilibrium, the temperature of the two streams is equal, but the mole fraction is not. That is also to be expected, and that is the magic that allows separations to occur. Once again, that's the point of the whole class, is being able to predict what the mole fractions will be for a given set of parameters. For a given temperature and pressure, what will the mole fractions in the liquid and vapor phases be? That would be this class distilled down into an extreme nutshell. Component molar fraction, I want ethanol again. So do the same component for both streams. You don't want to do the other component for the other stream. And then also point out, this is a mistake I see a lot. Students misconstrue what y and x are. Remember, y plus x in general does not equal to 1. So here I got 0.47 plus 1.6 if you round it. That does not equal to 1. It doesn't have to equal 1. It's ya plus yb is equal to 1. And if I were to also put component mole fraction of water in the table, you would see that that is indeed true. So if I double click here again and go to composition, these two numbers add up to 1. All right, let us now cycle through the various mole fractions of ethanol and measure the temperature and the composition of the two phases, and that will allow us to do the TXY diagram. So I'm going to go to Tools, and I'm going to, where is it? Case study is what I'm looking for. Sorry, not called the data book. It is called the data book, not case study. So data book. Let's see, insert. Yes, case is what I want. Maybe not. Nope, I was right. It is data book. Data book, insert, and then I want an object. So I have to pick a stream that I want to measure. So there's going to be 4 things I want to keep track of. I want to keep track of the ethanol flow rate. So that is going to be object ethanol, and the variable there is going to be molar flow rate. I'm sorry. I'm doing the same thing, but I want to keep track of it in a slightly smarter way. In my mixed stream, I want to keep track of what the mole fraction of ethanol is. It's basically the same thing. Remember, the flow rate of ethanol here is going to be the same as the mole fraction of ethanol in the mixed stream because of the way that I've defined them. In general, that's not true. But it makes more sense to keep track of the mole fraction of ethanol in the mixed stream. And that's like the overall mole fraction of ethanol. So I want to go to mixed stream and keep track of variable component molar fraction of ethanol. Okay. And then I also want 3 more variables. I want to do the mole fraction of ethanol in the vapor stream, in the liquid stream, and then the temperature. So in vapor, that object, I want to keep track of the component molar fraction. So scroll down in alphabetical order, component molar fraction of ethanol, and I'll add it. And if you add it, you can keep in the same window. I also want the temperature here. So you can choose the temperature from either the vapor or the liquid. It doesn't matter because it should be the same value anyway. Scroll down to T, temperature, add. I also want liquid. I got to scroll all the way back up. Should have done this before. Component molar fraction of ethanol. Add. Okay, good. All right, next. Object variable groups. I need to tell it what my independent variable is. Okay, now I need to go to case studies. This is what I was looking for earlier, and that's why I got confused. You may have to expand the window a little bit because when the window is crunched down here on the bottom, you gotta make sure you can see the whole thing. So I wanna go to case studies, choose what my independent and my dependent variables are. So my independent variable, the thing that can freely change, is going to be the mole fraction of ethanol. And why can't I click it? I need to add the case study. It's going to be the TXY case study. Add TXY. TXY. Can these be independent? Why can this not be independent? All right, it's not letting me select mixed stream component molar fraction as the independent variable. I'm not entirely sure why, but I have a guess that it doesn't like it for whatever reason. So over in my variables, I'm going to come over and do what I was going to do originally. So I'm going to delete that one. I'm going to insert, I'm just going to try and do it the old way with molar flow of ethanol. So not component molar flow here, just regular old molar flow. If I scroll down to the M's, and okay, it already went first. I wanted it to be first. Let's go to case studies, and for whatever reason, it likes that. So I'm just going to go with that. Remember, molar flow rate of ethanol is going to be the same number numerically because I set them to sum to 1. All right, so case studies is now finished. Now I need to sometimes I forget the steps involved here. Got it. Sometimes I just got to click around a little bit. So back to case studies and view is what I need. And now here is where I can set my lower bounds and my higher bounds. So my ethanol molar flow, I want to vary it from 0 to 1. It's going to go from 0 mole fraction to 1 molar fraction. And I could do a step size. I just like to choose 0.05. So that's the same thing of in Excel when you set the number of rows. So when I say X is going to vary from 0 to 1 by counting by 0.5, that's what that means. And then number of points should automatically fill to 21 because there's 21 data points between 0 and 1, counting by 0.5 inclusive. All right, hitting the start button here is going to run it. And it ran just now. Next, to see what it is, I need to click results. Now when I click results, this is not exactly a TXY diagram because for a TXY diagram, I need temperature on my y-axis and I need overall molar flow. So the x-axis is correct here, but the y-axis is not. So I need temperature instead. Unfortunately, you can't really do that in Unisim, so I need to export my data to Excel in order to plot it. So I do have to use Excel in some capacity. So click transpose table, very important. This table is useless. I need to click transpose table. I can just Control A to copy everything, Control C, then I got to go over to Excel and I need to stop my share and go over to share my Excel and Control V to paste it. And if I look at what my column headers are, this is my mole fraction ethanol. This column is my, what was it? I think it was my Y. I think it was my Y. This is my X, and this is my T. Oh yeah, I know for sure it's this one's Y and that one's X because in general Y is greater, and this is my mole fraction of ethanol, which is greater than mole fraction of ethanol in the liquid. Mole fraction of ethanol in the vapor is greater than mole fraction of ethanol in the liquid. All right, now I've got the data. Last thing to do now is to plot it. So I'm going to highlight my X and my T, go to insert. Good practice here would be to use this one. Why does it look like that? It's supposed to look like that. It might supposed to look like that. Not sure. I'm going to use this one just because it's a little easier to visualize. Remember that in general, when you have experimental data points, you want to use discrete data markers. And when you have a modeled data set, you want to use a line. So this implies that I'm fitting it with the model, which is not exactly true, but it helps to see it a little bit better. Let's put the Y on top. So I'm going to right click, select data, add series X values of Y's, and series Y value of T. And okay, that actually looks like how I expect the TXY for ethanol water to look. So at low mole fractions of ethanol, they are very different in terms of their volatility. And as the amount of ethanol increases, they almost converge. So a nice TXY is symmetric about either side, but this one is very asymmetric, right? Reflecting the non-ideality of it. There's supposed to be an azeotrope in here around 92% ethanol that we may or may not be seeing. I can't tell. We might not have good enough resolution on the plot. A good practice in doing this plot is to zoom in a little bit so you can see a little better. I don't want to zoom in that far. Let's say 75. Does that do the trick? Yep, that's good. And possibly this is an azeotrope. Again, we can't really tell. It could be because I need a different model. So you can experiment with different models as well. Maybe the Margulies or the general NRTL would work. So again, that is the TXY diagram. You can also do a PXY diagram in Unisim. So I'm just going to do that now at the risk of this video getting too long, just to make it a little bit easier to upload. I think it'd be better just to go ahead and do it all in one shot. All right, so to convert it to a, what did we just do? We just did a TXY. We want to do a PXY now. So in my E100, instead of specifying, I want to specify that the vapor phase is the same. That can remain. Oh, by the way, it'd be interesting to see what your data points are. You probably got different data points, but if you plotted the, am I screen sharing this? Okay, yes, I'm screen sharing this. Hopefully, if you plotted it, it should look the same, even though the data points are a little bit different. You just plotted different data points along the same curve. On my properties of my heater, nope. Conditions, nope. Design of my heater, nope. Parameters of my heater. There we go. Parameters of the heater. I want to get rid of the delta P constraint of 0 and add the constraint of delta T is equal to 0. And everything else should remain the same. Okay. And why am I getting 15.0004? What is the temperature here is 15. What's the temperature of my mix stream? Temperature of the mix stream is 15. That's odd. I thought it was a little bit below. Anyway, 15 is what I wanted it at, so that's fine, I guess. It's going to be the TXY for 15 degrees C. So already we see one data point. We know what the pressure is. I'm sorry, this is not an equilibrium. Hold on, I need to figure out what's happening here. Actually, I don't really know what's happening here. I'm going to try things in real time, and hopefully you can see my troubleshooting process. So I want to go back to Tools, back to my data book. Now, instead of temperature in my variables, I want to get rid of temperature because, oops, Tools, data book, Tools, data book. Not temperature here. I want to delete that one. And I want to insert for either vapor or liquid pressure. Okay, add. And let's just try it and see what happens. I don't think this stream is at equilibrium for whatever reason because the molar fraction of ethanol is 1. That doesn't seem right to me. Let me see what the mole fraction is. Okay, so the vapor phase fraction is 0.3. I can't remember. I think I set that. 100% ethanol. Doesn't seem quite right. Anyway, data book. Go to case studies. Going to add one. This is going to be my PXY case study. Independent variable is going to be the molar flow rate of ethanol. Dependent variables are the other three. View, varied from 0 to 1. Step size of 0.05. Start. Okay, maybe it worked. Let's go to results. Looks reasonable so far. Transpose table, copy. So select all, then copy. I'm going to put them over in Excel. Oops, and you can't see my Excel, so I'm going to stop sharing and share my Excel book. So this is my old data, and down below is the data that I just plugged in. So I'm just going to do a shortcut here and select the whole plot, copy, and paste the entire thing. And now I'm just going to drag down. So I'm going to click on a curve. A shortcut, if you already have a good format on a curve that you like, you can just highlight the data that you want instead of going through adding data. Okay, what happened here? Oh, my axis is constrained. I'll fix that in a minute. I need to do my other one too. So I need to do my other curve. And then because I set what bounds of my axis I wanted, I need to then go in and double click, axis options. And I need to go from, let's see, it goes from 1.75 bar to about 4.8 bar. All right, 1 bar to 4.5 bar. Okay, perfect. That is a PXY diagram. That looks funky. It does not look right to me. All right, I think I got it. Somehow my molar flow rate of ethanol got set to 1. I'm thinking when I ran that case study before, it reset, it just ended on 1. So I'm going to reset it to 0.3. And set it to 0.3, then that means my water should be 0.7, which makes sense. And now I've got a V that is about 0.46 and an X that is lower. So at least I'm getting not the component mole fractions of 1 that I was getting before, which makes sense. If I only feed ethanol to the system, then I'm only going to have ethanol. Let me just check a few more things. Checking my parameters is delta T is 0. This delta P is the change. Oh, that was something else I changed. I thought maybe the initial pressure was up too high, so I decreased it to 10 kPa. And so this delta P reflects 10 minus 2.06. So I'll just show you that real quick. 10 kPa instead of 100 kPa. I don't think that should matter as much, if at all. So if I click data book again and view, let's just try and rerun it. Oh, it sets it to 0, 1 there. Click results and transpose table. I compare that to what I've got from before. That is exactly the same as what I got before. All right, so maybe I'm just being neurotic. Maybe the PXY diagram is supposed to look like that. There is still an azeotrope, so that's good news. And again, it could be the fact that I have not the correct model that fits this system exactly well. It means it doesn't look exactly like I expect it to. Or it could be the fact that I'm just not as familiar with how the PXY diagram for water ethanol should look. I've spent a good amount of time staring at the TXY diagram for water ethanol, but not so much the PXY diagram. So I'm just going to stop share and adjust one more time, go to the Excel book just to show you what the diagrams look like. Now, if I were turning this in, of course, I'd clean these diagrams up, but just for other calculations to see what they would look like, this is sufficient. So again, this is the TXY diagram. Importantly, I have to specify what the temperature is for the PXY. So this is PXY at T is equal to, TXY at P is equal to 1 bar, and this is the pxy at t is equal to 15 degrees C. So finally, this video is concluded.